Good evening. Today, I will be covering food spoilage and food preservation. These actually are two very big topics. We should have bifurcated it, but maybe next year we'll do it. So, this is going to be a pretty long webinar, so you have to bear with me. So, if you look at food spoilage, what do you mean by food spoilage? It is a natural process, and you would have seen this. Generally, they will lose color, they will lose texture, and if most of you are the younger generation and you eat the chips, potato chips, lays and things, you will see that over a period of time they would have become they will not be crisp. So that is the texture. It would have become soggy. Flavor is there, where the flavor, especially if the oil has gone rancid, you will get a bad flavor or a bad aroma. Nutritional qualities also can degrade. The edibility, that means sometimes because of the spoilage, you cannot even eat it. So, consumption of any food spoiled either due to natural processes or due to contamination with micro organisms is dangerous, and it leads to illnesses, and they are a health hazard. The spoilage of food, any food, whether it is a fresh food or any other food, is a complex phenomena because it involves a combination of physical processes, microbial processes, and biochemical activities that take place in the food. In many food, they are still very active. Almost the cells are still living. So you will see these biochemical activities. And when the microbes are there, you have the biochemical activities of the microbes. So not only is food spoilage a health hazard, but it also carries a lot of economic significance, especially the post harvest losses, which lead to a loss in the agricultural produce. And most of it is either due to contamination or due to spoilage. So, if you look at the classification of food based on the shelf life, or rather the spoilage, you have three types of food. One is the perishable, which get spoiled very soon. These range from within days to 3 weeks. You can see, for example, milk. If the milk is not pasteurized and you have not boiled the milk, in the evening you will have curd. If you look at meat and poultry and you keep it at temperature, especially in summer when the temperatures range between 39 to 45, you will see by the end of the day they are spoiled. Bread is also one among the perishable foods. You see that you cannot keep it for more than 3 to 4 days. Either it loses its texture, the softness, or you will see mold growth on it. The second class is semi-perishable foods, in which the shelf life is a little longer, and you can keep those foods for about 6 months. Example, cheeses, potatoes, etc. Then you have the non-perishable, which you can keep for a very long time, which could be months or a year. And these include the nuts, flour, sugar, canned food, bottled food, mayonnaise, peanut butter, etc. So there are perishable, semi-perishable, and non-perishable. Then when foods are processed, and based on the processing, we can classify them into unprocessed or the minimally processed, where very little processing takes place, such as maybe just chilling, freezing, or maybe cutting, packing it in sealed packets, vacuum packed fruits, dried fruits or vegetables, some frozen meats, pasteurized milk, yogurt or curd. These are all either unprocessed or minimally processed. And then you have products which are processed, and they could be either heat processed or they could be frozen, or water removed from them. These include breads, biscuits, cake, ice cream, your soft drinks, jams, jellies, pickles, pasta sauces, um, ready to eat nuggets, your McCain's nuggets and things. So all these are processed food products. But irrespective of whether they are processed, semi-processed or unprocessed, they are all prone to spoilage, depending on how much care we have taken in the initial stages. So, what are the factors that affect food spoilage? So, the three factors that affect food spoilage are: they could be physical, they could be microbial, or they could be chemical. In the physical spoilage, there could be a change in the moisture content. Either it has lost water, gained water, or the water activity has changed. The temperature, due to an increase in the temperature or decrease in the temperature, some reaction in the food could have increased. It also depends on glass transition temperature and another physical property called crystal growth or crystallization. Microbial spoilage, all of you know that it is immense. These are caused by mold, yeast, and bacteria, and they not only are hazardous, but they could also cause a lot of food spoilage and food wastage. The chemical factors that can affect food spoilage are oxidation, there could be breakdown of protein, there could be putrefaction of the meat, there could be reaction between components of the food, Maillard reaction, there could be hydrolysis of pectin, and there could also be rancidity. You could have oxidative rancidity or you could have hydrolytic rancidity. So now just let us discuss these methods of, not methods, how the food spoilage occurs by these factors. So the first is moisture content. So what happens in moisture content is the degradation of the food product may occur, as I said, could be due to losing water, it could gain water, or there could be migration of water, migrating from one of the nutrients to the other. And this moisture transfer from one part of the food to the other part, maybe extracellular to intracellular, is directly related to water activity. We have seen when we had the webinar on water, what water activity was. It is a thermodynamic property of water, which is the ratio of the vapor pressure of water in a system to the vapor pressure of pure water, that is P by P naught. And we also give this as the relative humidity, where this is equal, it is a percentage, it is equal to the 100 into the AW. So we know and we have seen a list of products which have either high water activity or they have low water activity. In general, water activity of foods at normal temperature is, and water activity changes with temperature. So that is why you see these changes in the food also. So how does water activity change with the food? It is known that if the water activity of the foods at normal temperature is 1, whereas at -20 or -40, the temperature of the water activities could be 0.82 and 0.68, showing that water activity changes with the temperature. So now coming to what are the effects of changing temperature on the food? How does the food get spoiled? So the major effect of temperature is on fruits and vegetables. So you can see that cold temperature also will cause a damage to the fruit, and high temperatures also cause a damage to the fruit. So every fruit has got an optimum temperature and an optimum relative humidity for its ripening process. And if you look, those conditions of the optimum temperature and the optimum relative humidity are known as the modified atmospheres. And temperature is the one which actually besets the metabolism. So if you reduce the temperature, the fruits, the metabolic processes may be reduced. If you enhance the temperature to room temperature, the metabolic processes will increase, especially when enzymes are involved in the metabolic processes. You know that every enzyme has got an optimum pH and an optimum temperature to work at. Very often we think that low temperature or keeping in the refrigerator helps to preserve the food. But in many a case, it can also cause spoilage. So if you look at this banana, you see that if this banana is stored in the refrigerator, there is a damage. You see, this is the damage. This is a banana stored at room temperature. This is a banana stored at lower temperature. They can have a negative effect, and the freeze, if they freeze, freezing also can cause damage. So many a time at the lower temperature, the cells or this food will get frozen, ice will form, and these are the ice that forms tends to break the cells, and there is chilling injury. And this generally occurs before the food product starts to actually freeze at thing. So not all foods will survive when you freeze them or you chill them. So temperature plays a major role. High temperature also has an effect, and low temperature also has an effect on food spoilage. So on the lower panel, you can see the spoilage of cucumber, which has been stored at different temperatures for 9 days. So what you see is that which is stored at 15 degrees or between 10 and 15 degrees is better than what is stored at lower temperature. Then we come to a physical factor which is called the glass transition factor, glass transition temperature factor, which is known as TG, which affects the shelf life of food products. We know that foods, when you look at them, they are either the internal part of the food, they can exist as crystalline, semi-crystalline, or they can be in an amorphous state. So this state of the food depends on the composition of the solids, the temperature, and the relative humidity. So an amorphous matrix may exist either as a very viscous glass or a more liquid like rubber. So the glass transition temperature is the change temperature at which the change occurs from the glassy state to the rubbery state. Very often when you do grinding and when you grind, say, spices or some cereals, and the temperature goes up to very high temperatures, and then you remove the ground product, you will find that some of it would have clumped. That is because it would have changed from the crystalline state to the amorphous state. So this transition actually is a second order process, and the glass transition temperature varies from food to food. The glass transition temperature depends very much on how much of moisture there is in the food. So when you have higher moisture content, you will see that the glass transition temperature will be a little more higher. And it also depends on the relative humidity. So when dry foods are kept in a place with less relative humidity, they remain dry. But however, if you take them to the coast, such as Mangalore or Kerala, you will see that they will absorb water, and they will change probably from a crystalline state to an amorphous state due to this glass transition phenomena. So here is an example. So if the food is crystalline or semi-crystalline or amorphous, when you do any of these food processing techniques, such as grinding, extrusion, cooking, or gelatinization, or you do freezing, and you bring about a rapid cooling, that is a rapid change in the temperature, it can become an amorphous solid, or it can become dry and frozen. So the stability of the food depends on the composition of the food, the glass transition, the storage temperature, the relative humidity of it. And you will see that if the storage temperature is higher, then the glass transition of the relevant components, you'll see that there isn't much change. But if you increase the relative humidity, then you will see these changes. Then you have another factor which is called crystal growth and crystallization. So when you freeze a food, you see foods can undergo, the water inside the food will freeze, and the freezing will result in the growth of ice crystals, and these ice crystals will become large, and when they become large, you see here, they can either be intracellular or extracellular, and so they can actually damage the cell wall. The crystals grow, the water in it, they can damage the cell wall. So you can see a lot of these freezing, the spoilage due to freezing in a large number of fruits and vegetables. So in the freezing, if you do the freezing slowly, you will see that the crystal size is smaller. If you do a very fast freezing, you will see that the crystal growth is very hard. So you might have noticed that if you have actually frozen the fruit or vegetable, and then when you try to cut it, you will see that once the uh, ice crystals become water, the uh, firmness of the fruit or the vegetable will change. Crystallization can also occur when you have the product contains very high sugar content, and this you can very often see in ice cream. So if you have stored the ice cream at very low temperatures, or at not the recommended temperature, if the sugar content is very high, instead of having an ice cream, you might have a large amount of ice crystals, and that is because at that temperature the sugar will crystallize out. The sugar generally, when it crystallizes, it comes out to the surface and from the inside, and this is why you will see that gray or white appearance on foods that contain large amounts of sugar. The staling of sugar cookies, the graininess in candies and ice creams are all results of sugar crystallization. And sugar crystallization can be delayed by adding fructose or starch. And time plays a crucial role in sugar crystallization. That is, the longer you keep it, and depending on the temperature and the relative humidity, the sugar can crystallize. So the four physical effects are moisture, glass transition temperature, freezing, and crystallization. Now, microbial spoilage, we know, can occur due to the food product containing or being infected with bacteria, yeast, and molds. So bacteria causes food spoilage by biochemical reactions. You have yeast, especially growing in sugar containing, and mold will be growing where there is a lot of moisture. One of the best examples to find mold is that on a slice of bread. So microbial spoilage is brought about by these three microbes. So what are the factors which affect microbial spoilage? There are factors which are known as the intrinsic and the extrinsic factors, which can affect the microbial spoilage. And it is the intrinsic properties of the food which will determine the shelf life, expected shelf life, or perishability of the food. So we have seen this, and we have discussed this also when we did the water activity. So the other factors are the endogenous enzymes, the substrates, sensitivity to light and oxygen. These are the intrinsic properties of the food which can affect the microbial spoilage. The intrinsic factors later as we see, and it is these factors that we will use when we are preserving food, that is the pH, the water activity, the nutrient content, and the oxidation reduction potential. Although there are a large number of other factors, it are these four intrinsic factors which one looks at when you're trying to preserve the food or to extend the shelf life. The extrinsic factors, among them which there is a long list, the two major extrinsic factors are the temperature and the relative humidity. And these, the temperature and the relative humidity, uh, also dictates the presence, the growth, and the activities, the physiological activities of the microbes. So here is a list of the extrinsic and intrinsic factors. So you see the major intrinsic are pH, the type of acid present, the water activity, the redox potential, and the nutrient content of the food. In the extrinsic, the major factors are temperature, so that is the external temperature, the relative humidity, and what type of packaging material you use. I will not be discussing anything about the packaging material because you have a whole set of webinars on packaging. But the food processing also is an extrinsic factor. How the food is stored, how the food is distributed, and what are the hazard analysis at critical control points, whether they have followed HACCP, whether they have followed GMP, GLP, etc. These are all the extrinsic factors. Now, we can control both the intrinsic as well as the extrinsic factors to preserve the food or to enhance the shelf life of the food. So, if you look at the molds and yeast, so what is the conducive temperature and relative humidity and water activity for their growth? So you see molds can grow between pH 3 and 8. They can grow across a wide range of temperature. That means they can grow at ambient temperature to a little higher temperature. The molds can grow in foods which have a water activity even as low as 0.62. But the molds are heat sensitive. So if you heat the food product, and you can kill all the mold spores of the mold or the conidia of the mold, you can prevent mold formation. So the foods that are generally affected are bottled mineral water, fermented food, bread, cakes, and pickle. Yeasts again grow in a very broad range of acidic pH. They grow across a wide range of temperature. So these are one of the microorganisms which, while preserving food, it is quite difficult and you have to use a large or very different technologies to control the yeast. They, however, they grow only when the water activity is above 0.4. So one of the criteria that can be used for enhancing the shelf life is to decrease the water activity to below 9. They are heat resistant and they can even survive under scorching sunlight. So the affected foods are mainly the fermented foods. So the growth of most microorganisms, bacteria I haven't included here, we will see them later because each bacteria has got its own conditions where there is optimal growth. But the growth of microorganisms can be prevented, that is molds, yeast and bacteria can be prevented by controlling the storage temperature, by reducing the water activity, by lowering the pH, by using chemical preservatives, and by using proper packaging conditions. So here is a table which shows you the fungal spoilage of starch-based foods in relation to the water activity. So just let us look at rice or the glutinous rice, which is a cooked rice. So you see when the water activity is very high, 0.98, the maximum time you can keep it is 7 days. Whereas when you reduce the water activity to 0.65, you can keep it for about 73 days. So rice flour, this is glutinous rice, not cooked rice. Rice flour, you see, if the water activity is 0.9, maximum you can keep at 11, you will see there will be a mold growth and you will have musty odor. However, if you reduce, that means if you remove the moisture and you bring down the water activity to 0.65, you see that you can keep it for more than a month, and for even up to 6 months, you see there is no fungal development. So therefore, the growth of the fungus depends on the water activity, and by reducing water activity, you can enhance the shelf life. So here are the tables. You are not expected to remember all this. So here this gives you the conditions of the major food pathogens which are regulated and it should not be present in food. So you see salmonella, it grows, the optimum temperature is, it grows anywhere between 35 to, the optimum temperature is 35 to 43, but it can even grow at 4 or 47. The optimum pH is 7 to 7.5, but it can grow between 3.0, 3.8 to 9.5. So maximum is 0.94. So if you reduce the water activity, salmonella growth will be inhibited. If you add salt, 4% salt, you can inhibit salmonella activity. So the gas, for allowing, it is a facultative organism. So similarly, you see, for all these organisms, you find the optimum pH, the optimum temperature, and what the water activity is. So what is important over here is to look at these toxic organisms such as Clostridium botulinum also. So you see this can grow even if you keep it in the refrigerator, 10 degrees Clostridium botulinum can grow. It can grow in acidic foods and it can grow in high water activity. So we have to reduce the water activity. Among the water activity, it is generally said that below a 0.87, most of the microorganisms will not grow, as seen in this you can see, except for Campylobacter, not Campylobacter, except for Chronobacter, which you see that Chronobacter can grow even in absolutely dry foods such as dry powders. So Chronobacter, if you look at FSSAI regulations, you have to um, look for Chronobacter. You have to do microbial analysis for Chronobacter, especially in infant food, that is the infant baby powder or the milk powder. That is because it can even grow when the water activity is about 0.2. So what are the effects, the spoilage effects, and the bacteria which are associated with them? In meat, you see, it can undergo putrefaction or it can undergo souring. So these are the spoilage microorganisms. Cured meat, that is meat which is treated with salt, can also become moldy. Souring can take place and it could be slimy. Even vacuum packed meat, it can undergo souring and greening, and the lactobacillus and leuconostoc can grow. Poultry, generally you get a bad odor and slime formation. Dairy, you see everything, right from taste to smell to appearance. So here you see bitterness in dairy products such as cheese and thing is because of Pseudomonas. Souring of milk is due to Lactobacillus thermophilus. The sweet curdling is due to Bacillus ceres. If you have the black discoloration on cheese, it is due to Candida. And you have a gassy cheese, which is due to coliforms, lactic acid bacteria, and Clostridia. Fish, very often the spoilage is putrefaction, which is caused by these three bacteria. Eggs, you can have green rot, colorless rot, or fungal rot. In fresh vegetables and fruits, generally you have the soft rot. So if you have observed some of the fruit, fresh fruit and vegetables from the refrigerator, you will see that they would have undergone rotting like this, and there will be a fungal growth over here, fungal or a bacterial growth. So you have bacterial soft rot, gray mold rot, rhizophus, etc. And if you have forgotten your fruits or vegetables such as cucumber and apple in the refrigerator, after a month or so, you will see this appearance of the fruits like this. Canned fruit can undergo souring, and this is caused by the flat sour organisms or the rope forming organisms. You can also have a smell which is due to Clostridium. You could have butyric acid fermentation. You can have sliminess because of yeast and molds. And bitterness in wine could be due to Acetobacter or Enococcus. What are the chemical changes that are caused by the microorganisms? There are numerous chemical changes that these microorganisms cause because they use the food as a substrate, and they bring about degradation of that food. So they can degrade carbohydrates and bring about fermentation. They can degrade the nitrogenous compounds by proteolysis and produce amines and things which are give a very bad fishy odor. They could degrade lipids to give you oxidative rancidity or hydrolytic rancidity. They can cause softening of the foods by bringing about pectin hydrolysis. So just I'm going to give you a few examples. So if you look at the carbohydrates, they can break down the lactic acid or the glucose to lactic acid, and from lactic acid they can produce 1,2-propane diol. Or from the lactic acid they can uh, make pyruvic acid by lactate dehydrogenase. Pyruvic acid is converted into acetyl CoA, and acetyl CoA can be oxidized to acetic acid or vinegar. Also, acetyl CoA can be converted into acetaldehyde and you might get ethanol. So there are large number of degradation. And later on in the slides, we will see the different types of fermentation that the microorganisms can bring about. The microorganisms can break down proteins into peptides and into amino acids because they produce a large number of proteases or proteinases, which will break down the proteins. So what it results in when these nitrogenous compounds are broken down is putrefaction, or the bad smell that you observe. So the bacteria, when they bring about the degradation, you see they can produce volatile products which give you a very bad smell. So cysteine D sulfidase acts on the cysteine and it can produce hydrogen sulfide. The methionine lyase can act on the amino acid methionine and bring about a methyl mercaptan. So those of you who have used mercaptoethanol in electrophoresis will know how bad it smells. So lysine can be decarboxylated and you can get these awful smelling, very fishy smelling diamines, which are cadaverine, putrescine, histamine, spermine, and spermidine. So the degradation of nitrogen compounds brings about putrefaction, and the aroma is very bad. In fish, mainly the microorganisms which infect the fish act on trimethylamine oxide. The trimethylamine oxide reductase acts on this and it produces trimethylamine, which again has a very fishy odor. Mercaptoethanol may be tolerable, but this fishy odor is not tolerable. And all these off flavors which are produced in foods are due to different chemical compounds. So you see trimethylamine gives you the fishy odor, the dimethyl trisulfide gives you a garlic like odor, dimethyl sulfide gives you a cabbage or that brassica odor, esters give you a fruity odor, ethanol gives you that alcoholic odor, diacetyl acetone gives you the cheesy or the buttery odor. It is produced in meat. Then you have a medicinal odor, and also sometimes you can smell the souring because of the acetic acid, lactic acid, or citric acid that is produced by the microorganisms. Uh, in the case of spoilage, you have an effect on the texture. So when you have the slime, where it is slimy, then it is the breakdown of a polysaccharide. When it is softening, it is the breakdown of the pectin. When there is curdling, especially in milk, it is due to the presence of lactic acid. And if you see holes in the product, especially the cheese, it is due to the carbon dioxide. Visual problems, especially you see bloating in a packet of curd or in a packet of milk, it is due to gas production. If you see holes also, it is gas production. And if you see can swelling, any canned food which is worn, it is generally there is an anaerobe inside there. And I mean, there is an organism which is producing a gas, and that is why the can will smell. So many a time you will see, especially in the case of dairy products and juice, the fruit juices, it says if you find the pack to be swollen or bloated, do not buy, indicating that means there is a microbial contamination, and it is a microbial contamination which is causing the bloating of the container. So chemical spoilage. Now coming to chemical spoilage is generally due to biochemical reactions, and it could be because of an enzyme, it could be because of a change in the pH, it could be because of the oxidation of lipids, and the discoloration. It could be enzymatic browning. It could be autolysis, breakdown of its own products, again pectin degradation and Maillard reaction. So in the case of microbes, the pectin degradation was due to the pectinases which were produced by the microbe. But in case of chemical spoilage, it will be due to the degradation of the endogenous enzymes which are in the product. So enzymes that cause food spoilage, you see, ascorbic acid oxidase, which destroys vitamin C. Lipase, if it present, it will bring about hydrolytic rancidity. Lipoxygenase, if produced, it will destroy vitamin A. Pectic enzymes will break down the pectin, that is softening of the fruit. The peroxidases you see will cause browning. Polyphenol oxidase in fruits and vegetables causes browning and off flavor. Proteases in the eggs and thing cause the reduction in the shelf life. Over tenderization. Thiaminase in meats and fish will destroy the thiamine. So if you look at the basic enzymatic browning reaction in a fruit, especially if you take an apple or you take a potato or you take a brinjal, the eggplant, when the apple is intact, the phenolic substrate and the enzyme, the polyphenol or oxidase, are in different compartments. When the apple is cut, the polyphenol oxidase and phenolic substrate come in contact with each other, and when it is cut, it is exposed to atmospheric oxygen. Then the hydroxylation of the monophenols in the apple first takes place, and it forms a dihydroxy phenol or a catechol. And on further oxidation, because large amount of oxygen is present in the presence of the enzyme polyphenol oxidase, the catecholase part of it, you get a quinone, and then you get water. And this brown products that you see are due to the quinones, that is the orthoquinone, etc., which are produced. So enzymatic browning is very common in products which contain fruits and vegetables. Then you also have the browning, which is caused by the metabolism of tyrosine. And we have seen that when tyrosine is metabolized, it can undergo a metabolization to form the melanin pigment or the brown pigment, and this causes the black or brown coloring that you see. It goes through the pathway. Tyrosine is converted into dopa. Dopa is converted into 5,6 dihydroxyindole, then into the quinone, and you have melanin. And you know that in this pathway, in the humans, when there is the deficiency of the enzyme in this tyrosine pathway, melanin is not formed, and what you see is the albinism. Okay, so similar pathways are there. So melanin pigments also can cause browning. In the case of autolysis, this takes place, the word autolysis itself says the breakdown, self breakdown. So if you look at in fish muscle, what happens? In fish muscle, when the fish is sacrificed, caught and sacrificed, you will see that ATP, that is the energy unit, is broken down into IMP and into a bitter off flavor. The fresh seafood flavor is because of the IMP, that is the inosine monophosphate. In the case of the autolysis, the glycogen, which is the storage carbohydrate of the fish, will be broken down into glucose. Glucose will be broken down into lactic acid due to the anaerobic pathway. And then because lactic acid is an acid, it brings down the pH. When it brings down the pH, it causes denaturation of the protein and destabilization of the protein. And also, when it changes the pH, it alters the enzyme activities, either allowing the enzyme to act or not allowing the enzyme to act. So, there is a cascade of reactions, especially in the postmortem changes of fish muscle. You also have where ATP, when it is broken down, ATPase breaks down ATP into ADP. The myokinase converts it into AMP. Then a deaminase converts it into IMP, and IMP is converted into inosine and hypoxanthine, which give you the other flavors that you can see. So autolysis in any meat or fish is due to the breakdown, is due to more than one pathway. Then, as I said, the pectinases, that is the softening of the fruit, also is due to a chemical reaction of the enzymes which are contained within the fruit. So if you take an unripe mango, you will see that it is a climacteric fruit. It will contain the enzymes ACC synthase and ACC oxidase, which produce ethylene, the ripening hormone. So this ripening hormone will bring about biochemical changes, molecular changes, and it will, you have the organoleptic properties will change. Also, during this ripening, what you will see is the pectin is in the form of a protopectin. The enzymes pectin methyl esterase or pectin galacturonase and other carbohydrate breaking enzyme will break it down into soluble pectin, and the soluble pectin will be by the action of the pectin methyl esterase will cause the softening. So ultimately what happens is the fruit from unripe to the intermediate to ripe, and then from ripe it becomes overripe, and finally you have a spoilage of the thing. So one way of preventing the spoilage of these is to actually add calcium to it, where the calcium complex, EDTA will chelate the calcium and prevent the pectin methyl esterase from acting. So the endogenous enzymes also, with the time, that is with the temperature, optimum temperature and pH, can get activated. Rancidity, we have seen when we look at it, it is caused by lipase. So you have a triacyl glycerol, and soon as moisture is available to it, it can be broken down into glycerol and the fatty acid, and it is this fatty acid which gives the bad smell or the rancid smell. You have oxidative rancidity, where when the food gets exposed to oxygen or oxygen is available, it is the linoleic acid, the enzyme lipoxygenase, which will be an endogenous enzyme, can break the linoleic acid into hydroperoxides and into the compounds which have a bad smell, which gives the rancid smell, such as hexenol and aldehyde. So you have oxidative rancidity if oxygen is present. If moisture is present, the lipase will bring about hydrolytic rancidity. You can also have a reaction, another non-enzymatic browning reaction, which is called as the Maillard reaction. The Maillard reaction occurs between a carbohydrate and a protein or an amino acid to form what is a Schiff's base, and this Schiff's base is brown in color. So you have the Maillard reaction, and if you have brought about heating, this enhances the Maillard reaction. So the browning of the dosa that you see when you make crisp dosa is due to a Maillard reaction. The caramelization of sugar, those of you who like caramel and caramel custard, you will see that the caramel that is formed is when the sugar reacts with the amino acids under heat to give you the caramel color. Caramel color is nothing but the brown color. So when you have these chemical reactions, not only can do you have the Maillard reaction and the Schiff's base being formed, you will see that in the presence of other amino compounds or the chemistry of it is the Schiff's base forms, and that will undergo an Amadori rearrangement, and these Amadori products can either be broken down into acetol, diastole, and pyruvate. They could be reduced, or they could form what is known as hydroxymethyl furfural or furfural by the dehydration reaction. So all these products, that is the HMF or the furfural, all these Amadori rearrangement products, the aldimines, the ketamines, etc., will give you the brown color or the brown nitrogenous polymer, which are known as melanoidins. And this is responsible for that nice brown color that you see in your dosa. Now we have looked at what are the uh, mechanisms by which food is spoiled. Now we will look at how food is preserved. So how do we preserve this? So this refers to the process by which we can prevent food spoilage and increase the shelf life of the food. So changing the raw products into more stable forms that can be stored for longer periods of time is what is required today. And this allows any food to be available at any time of the year at any part of the world. So if you look at the different preservation and processing techniques, here we have chemical processing, biological processing, and you have physical processing. Very important are in the physical processing, the thermal processing and the non-thermal processing. And in the non-thermal processing, uh, among these processing techniques, the thermal processing, where you use pasteurizing, sterilizing, or the hurdle technology is very important. And in thermal processing, where you remove the heat, you can, in the cold treatment, freezing, refrigeration, and chilling are very important. And many foods have been preserved by these processes, not only by the physical processes, but by a large number through the chemical processes. And we have seen that when we talked about the food additives, and we saw the section on preservatives. So drying is one of the most primitive forms of uh, preservation, food preserving. And by now, all of you should be knowing that moisture is a major culprit. The water activity is a major player in the spoilage. So if we can reduce the moisture content, if you can reduce the water activity, you will find that the food will be stable and the shelf life increase. So water can be removed by a process which is known as drying, and that is common, and you need no explanation for that. So most microorganisms can grow at water activity greater than 0.95. So they are inactive at 0.9, but they cannot grow below 0.88 except chronobacter, what I told you. So therefore, if you do drying by any method, using oven drying, etc., you can preserve the food. But the disadvantage here is you may lose flavor, you may lose aroma, and there might be losses in some in vitamin C, thiamine, protein, etc. The protein gets denatured. So the drying methods, you have ovens. So you can have a convection type of oven, or a conductive type of oven, or a radiative type of oven. Industrial dryers are available, and you can have batch dryers where you can keep them for a short time, or you have continuous dryers where they have for very long periods of time. So what you have over here is a plate dryer. So you see the food is put in plates and it is dried by enhancing the temperature. And here you have a vacuum oven dryer. So fruits, vegetables, meat, fish can all be dried. So also coffee and tea, which have been dried by techniques which are known as spray drying and freeze drying. So what is spray drying? Spray drying is a technique which is carried out by a special equipment. And here the food or the liquid is introduced in the form of a spray or as fine particles through an atomizer atomizer as a fine spray, and then you will see that heat waves or heat, there will be some thermal treatment, and this causes the water to evaporate. So all spray dryers use an atomizer or a spray nozzle to disperse the liquid into a fine spray. Then some hot drying gas or air is passed in the same direction as this spray. And as a result, when the hot air flows, water evaporates, and the particles with with uniform size and shape will can be collected. And this spray drying technique is used mainly for milk powders. You will find coffee powder. All these are spray dried, and they are also used for coating and encapsulation. Another drying method is known as freeze drying, or generally done in a large number of research labs, which is known as lyophilization, but it is done for foods also. Here, instead of in spray drying, the food is introduced as a spray. In the case of freeze drying, the food is frozen before it is dried. If you look at the freeze drying process, what happens is when the water is frozen and then it is subjected to a vacuum, that is when the pressure is brought down, you will see that water will go directly from the frozen state, that is from ice, to it will vaporize. It will not go through the liquid state, or this is called as sublimation. So what is the other example of sublimation? I know I can't see you, but iodine is one of the only elements which does not go through the liquid, and it sublimes. But water in the freeze drying process goes through a process of sublimation. And why sublimation occurs is, if you look at the phase diagram of water, there is a point which is called as the triple point, and at that particular pressure and temperature at the triple point, you see it goes from the solid to gas. So it can go from solid to gas. It need not go from solid to liquid to gas. So these are this triple point of water. It takes place at 4.579 millimeters of mercury and 0.009 degree Celsius. Okay, so coffee or coffee powder, the instant coffee powder that you have, Brew or Nestle, they are freeze dried products. So that is why when you open a bottle of instant coffee powder, you see that if you do not keep it airtight, it will easily take moisture, and then you have a hard, all your coffee powder is in one hard lump and cannot be used. That is the disadvantage of freeze dried products. You have to keep them tight and um, free or free from moisture. So now a large number of fruits, vegetables, dairy products, etc., can be bought as freeze-dried products. So the freeze-drying process, in the case of a soup, if you look, it's all mixed, the ingredients are mixed, it is frozen, and then it is freeze-dried to remove the moisture. The applications are numerous. You can freeze dry almost anything which has water in it. Then we come to a very important preservation process, which is known as pasteurization, and the other one is sterilization. This is a physical preservation technique, and it is named after the French scientist Louis Pasteur, who actually found out that by pasteurization he can prevent the spoilage of beer. So he found out that if you heat the beer to a certain temperature, it would there would be no spoilage. And almost in the case of pasteurization, you will see almost all the pathogenic bacteria, yeast, and molds can be destroyed, and the shelf life will be increased. So, pasteurization for different foods, you see, fruit juice. What the main purpose of pasteurization is to inactivate the enzymes. The secondary purpose is to prevent microbial growth. And you see that the typical temperature time combination which is used because you want to prevent the growth of salmonella and the cryptosporidium parvum. If you see, it is 65 degrees for 30 minutes, or 77 degrees for 1 minute, or 88 degrees for 15 seconds. Now we need to understand why we have these particular temperature and time combinations. So for beer, you see it is 65 to 68 for 20 minutes, and or 72. Here it only has to prevent the growth of the spoilage microorganisms. So you look at milk, we need to destroy the spoilage microorganism. So you have 71.5 for 15 seconds. So let us understand why we have these things. Uh, in the next few slides, I will explain it. But in the pasteurization techniques, these pasteurization can be done by a batch process, by using a vat where it can hold large amounts, 100 to 500 gallons of the liquid, and it is pasteurized. So at a particular temperature and the particular time point. And this time and temperature depends on, or it is mainly based on, the thermal dead time studies of these heat resistant microorganisms. And we will try and understand what is this thermal dead time. You also have, under pasteurization, high temperature short time, or it's called HTST, also known as flash pasteurization. And then you have UHT, ultra high temperature, which increases the shelf life further. And so the heating is done, and then the products are aseptically packed. So the UHT products, I don't know how many of you are buying the UHT milk. Nandini makes Good Life, which is in the packets, which are in pouches. You can keep them for almost 8 to 9 months at room temperature, unopened. Once you have opened, you have to refrigerate, or you have to consume the whole packet. That is the UHT pasteurized products. So this extent of this temperature time combinations, how did they arrive at these? So if you look, pasteurization treatment for the first time actually was extended to milk pasteurization. Historically, it was due to the milk pasteurization to actually kill or prevent the growth of Mycobacterium tuberculosis and Coxiella burnetii, because these were the emerging pathogens then. So Now, if you look, there are some definitions we need to know about for pasteurization and sterilization. So, what is sterile? Sterile means it is free from viable microorganisms. So, those of you who are working in microbiology labs know that you have to sterilize all your media, all your equipment before you do to uh, to see that the results you have got is due to the analysis you are doing and not to the microorganisms which are there. You have sterilization, which is any physical or chemical process which destroys all life forms with special regard to microorganisms, including the bacteria and the sporogenous microbes. Thermal death time. Thermal death time is defined as the time that is necessary to kill a specific number of microbes at a specific temperature. So this value is obtained by keeping temperature constant and measuring the time necessary to kill a certain amount of cells. So we will see this thermal death time and we will see the thermal death curve. And then you have the D value, which is known as the decimal reduction time. The D value is defined, or it denotes the decimal reduction time, which is the time required at a specific temperature and under specific conditions to bring down the microbial load by 1 decimal or by 1 log. Okay, so it is 1 decimal or 1 log. The decimal reduction time is dependent on the temperature and type of microorganism. So different microorganisms will have different D values at different temperatures, and that is why you use these. That is why you use the different temperature and time combinations for the different microorganisms that you want to kill. So D value is very important when you're doing food preservation or preservation by pasteurization. So D value is defined as the decimal reduction time. It is the time required at a specific temperature under specific conditions to reduce the microbial load by 1 log or 1 decimal. 1 log and 1 decimal are the same. So if you look at the thermal death curve, that is, if you plot the time versus the number of living bacteria by measuring it, this is the number of living bacteria, and you see on this axis we have the log 10 log values of this. So the thermal death curve, this is known as the uh, thermal death curve. So we said D value is the time required to bring down the bacteria population by 1 log or 1 decimal. So let us take this at 40 minutes. You see we have 3 log. Now at 4 log, you get to decrease from 4 log, to decrease the bacteria from 4 log to 3 log. You see 4 log, the time required is 26 minutes, and the time required by the time it comes to 3 log, it is 40 minutes. This is at a particular temperature. So the D value is 40 minus 26, which is 14 minutes. So it is the time taken required to destroy 1 log cycle or 90% of the pathogenic organisms under the reduction cycle, and this is known as thermal reduction. If it is 12 cycles are reduced, it is called 12D. If only 1 log is reduced, it is called 1D. So the heat process for pasteurization of milk or any food product is based on a 12D concept. That means the heating process should reduce the microbial population by 12 logs. I hope that is clear. So the term D value, as we say, is the amount of time that it takes at a certain temperature. In other words, it is to kill 90% of the organisms being studied. So thus, after an organism is reduced by 1D, only 10% of the organisms remained. The second, in 2D, there will be 90% of this remaining. So the D values always, when it is given, because they are given for specific values and at a specific temperature, you will see that the D value is written as, so the D value is 121 degrees centigrade is 2 minutes. So therefore the time required to bring down the microbial population by 1 log at 120 degrees is 2 minutes. Okay, so for heat inactivation we write it this way, and for radiation inactivation we give it in terms of the irradiation dose. So the D value can be determined graphically, as we have seen, or you can use it, get it numerically from this equation. D is equal to T divided by log of N naught minus log of NT. Okay, so here what was the log at 0 time? What was the log at, now at 0 time? It's the temperature, and minus log of this temperature, and T is the difference over here. So if you see, the difference we see is 14 minutes, and then you will have log n naught. So log n naught is 4 and log nt is 3. Therefore 4 minus 3 is 1. This t is 14 minutes. So the d value is 14 minutes. So now if you look at the comparison between the different pasteurization techniques that we use, so if you see VAT and you see the high temperature short time, so you see it is based on that 12D reduction. So it is 72 degrees for only 15 to 30 seconds. In VAT, it is 65 for longer time. And in the ultra high temperature, you see it is at much higher temperature for only a few seconds. However, when you look at these pasteurization process, high-end pasteurized process techniques such as the continuous processes of HTST and UHT bring about some changes in the nutrient content of the food, especially vitamin C, calcium, phosphorus, thiamine, and vitamin B12. So you can pasteurize buttermilk. So that is why you see, you get Amul buttermilk. You can pasteurize frozen desserts, fruit juices. You can pasteurize milk. And if you look at comparing the shelf life, the VAT process, it increases the shelf life to several days when refrigerated. The HTST, it increases it by 2 to 3 weeks, but UHT, you see, it increases it to month, and you can keep it in at ambient temperature. So now trying to understand why the pasteurization is being done by HTST. We look at the curves. Okay, we look at a curve which plots temperature versus the heating time. So this is to decide the time and the heating temperature that one must use. So if you look at this graph shows the temperature versus the heating time for the pathogen. And so above this line, you see all the pathogens are destroyed. Now, this line here tells you what happens to the vitamin at this temperature and this heating time, because in a preservation process you want to kill the microorganisms, yet you want to retain the nutrients. So now if you see this curve, above this curve it's destroyed and not destroyed, so we need to work here for the microorganism. But if you look at vitamin, above this it is destroyed and below this it is destroyed, so we need to work in this region. And the only two intersecting region of this is here. So this is the region that can be used for high temperature and short time. So you see the high temperature ranges from 100 to 110 degrees, and the short time could be as less as 3 minutes to zero point 0.3 minutes, which is a few seconds. So 0.3 minutes is about 18 seconds. So by using these type of curves, they can determine what temperature and what time must be used for the high temperature short time pasteurization of the product. So if you look at high thing, you see they have used 72 degrees and they have used 15 to 30 seconds. And what you see over here is this, which comes to less than 100 degrees or so. So you can determine the high temperature and the shorter time process. Then what is this 12D process? As I said, the 12D process, D is the time taken to reduce the microbial population by 1 log at a particular temperature. The 12D process is, it is understood that if you reduce the microbial load by 12 log, it is that all the microorganisms are killed. Especially so in the case of canned foods, where you have Clostridium botulinum. This organism can cause botulinism, we have seen. The spores actually can survive very high temperatures or heat treatments, and so therefore it is assumed, or the food technologists have decided that if you use 12 logs, that is a 12D at 250 degrees Fahrenheit, there will not be a single spore, surviving spore of Clostridium botulinum. So this process is based on the assumption of the number of surviving. So if you assume there are 10 surviving spores in one can, then we can calculate the time for a 12D process to occur by using the this formula, that F naught is equal to D250 log A minus log B, where A is the initial population and B is the final population. So you have the F naught is 0.21, you have 1 log minus log 10 to the power of minus 11. Nothing should survive. And this is actually known, the result is the 12D process. That is the time taken to reduce the number of surviving spores by 12 log. And then you have another term which is known as the Z value. So this Z value actually is obtained by a graph for plotting the temperature versus the D value. Okay, so you determine the D value and you plot it against the temperature. So the Z value is defined as the temperature change required to change the D value by a factor of 10. So if you look at this graph, if you want to change the D value from 3 to 30, and then you see for 3 it is 100, for 30 it is 90. So you have to have a difference in the temperature of 10 degrees. So reactions that have got small z values are highly temperature dependent, whereas those which have very large z values require larger changes in temperature to reduce the time. So if you look at this, you have lower z value, so you have lower d values. This is at 121 degrees Celsius. And when your z value is much higher, you see you also have higher d values. So the z value is defined as the temperature change required to change the d value by a factor of 10. So the z value, this gives you an indication of the impact of different temperatures on the microorganism, with smaller values indicating greater sensitivity to increasing heat. So the z value can be obtained by plotting the logarithm of the at least 2d values against the temperature, or using the formula z is equal to T1 minus T2, which is the temperature, and D1 and D2 are the logs of the D values. So you can obtain the Z value. So here is a working example and how to use the D and the Z values in pasteurization. So the problem is pooled raw milk at a processing plant has a bacterial population of 4 into 10 to the power of 5. It is to be processed at 79 degrees Celsius for 21 minutes. The average D value at 65 for the mixed population is 7 minutes. I want you all to pay attention to, you see, the temperature, the time, and also here the organism is not given, but it says the average D value is for a mixed population. So that is for all the microorganisms is 7 minutes. The Z value is 7 degrees centigrade. So how many organisms will be left after pasteurization? So now let us work the problem. You have the temperature is 79 and the D value is D value has been reduced by 2 log cycles from that at 65. Okay, because if you see the temperature difference between 65 and 79 is about 14 degrees. So the D value has been reduced by 2 log cycles from that at 65. Okay, so you see at 65 it is I think 7 minutes. So at 79 the temperature it would have reduced by 2 log. Now hence it is now 0.07 minutes. The milk is processed for 21 seconds. So 21 seconds, you must convert it into minutes. So it is 21 divided by 60, which is equal to 0.35 minutes. So in 1 minute, the D2 will, the Z value is 0.07. So if the Z value is 0.35, what will the reduction be? That means it will accomplish this 5 log scale reduction to 4. Okay, so that it would think. So at 65, you would need 35 minutes to accomplish a 5D reduction. So if you look at the previous formulas and you understand what is D and Z, then you will understand how to do this problem. So the thermal sterilization based on pasteurizing or anything can later be subjected to retorting or to aseptic processing. And these details I'm not go into detail. It will be taken up with packaging. But retorting and aseptic processing are that in addition to the sterilization or the pasteurization, you add another step, that is, you used aseptic packaging, or in retorting, directly you pasteurize in the container that you're going to keep it in. So, in thermal sterilization, there are two categories: retorting and aseptic processing. So what are let's compare what is pasteurization and sterilization. So at the temperature level, you see pasteurization is generally carried out at 65 to 75, except the UHT, which is carried out at higher. Sterilization can be carried out by various temperatures, which include 135 to 140. So what happens to the heat resistant? Most of the heat resistant microorganisms and things may remain alive, but in the case of sterilization, you will find that they are almost all removed. The effect on the nutritional capacity and profile: pasteurization, you have negligible, but sterilization results in the loss of calcium, minerals, and vitamins. Storage: after pasteurization, you must store it under refrigerated condition. But after sterilization, it can be stored under ambient. So this, and very good example, is the milk that you buy every day, which you get in pouches. So you see that if you do not boil the milk by the end of the day, the milk will be spoiled. However, if you can keep it in the refrigerator, you will see that it doesn't get spoiled. And the shelf life extension is a few days or weeks, and in sterilization, it is much, much longer. Then you have the other technique of preservation, which is freezing. And this action of freezing, or the process of freezing, will not sterilize the food. However, the temperature is like 0 degrees Fahrenheit or minus 18 degrees colder. This stops the growth. It doesn't prevent the growth. It stops the growth of micro organisms, and it also stops or retards the chemical changes and the enzymatic reactions, because you know each enzyme has an optimum pH and an optimum temperature. So freezing will not preserve by sterilization, but freezing will only preserve by inhibiting or retarding the growth of the microorganism. So in this unit operation of thing, the temperature of the food is reduced to below its freezing point. Whatever water is in the food will be converted into ice. And how do these ice crystals form? When it is being frozen, the water which is there in the food will get mobilized to the ice. And because the water is removed and it is goes into the ice, when freezing happens, the water activity of the food is reduced. And when water activity is reduced, the microorganism growth is inhibited. So here the preservation by freezing is achieved by using low temperature and by reducing the water activity. So freezing food, the frozen food can be kept for a very long period of time, about 3 months. Deep freezing is the reduction in temperature, where the microbial activity completely ceases, and a freezer should generally be kept at minus 18 to minus 25. So what is the effect of freezing? Generally, the effect of freezing a food does not have any effect on the nutritional quality, other than the vitamin C and thiamine may be reduced if you have a blanching process, that is immersing it into boiling water before you freeze. You know, the frozen peas and the frozen vegetables that you buy are all initially blanched and then subjected to freezing. Fish, if it is frozen slowly, some of its cells rupture and they will release the nutrients. So when you defrost the fish, you will see there is a lot of water, which is known as drip loss when the fish thaws. So in some cases, the flavors become stronger. In some cases, the flavors are lost. So in freezing, what is important is the time of freezing. So if you have slow freezing, this results in the formation of larger ice crystals in the extracellular spaces. If you do rapid freezing, you have a larger number of small ice crystals which are distributed throughout the tissue. So, what is the impact of this? So, here, if you do in a food which you have done the rapid freezing, you have more crystals, it could lead to damage to the tissue. Okay, so yeah, when freezing occurs, it depends on first a small ice crystal will form, which is called nucleation, and then the ice crystal will become larger, and it is known as the growth of the thing. So remember that slow freezing results in the formation of larger ice crystals, and rapid freezing results in larger number of smaller ice crystals. And freezing can be done by different methods, which is air freezing, indirect contact, and direct contact. So air freezing is the cheapest, in which you force some frozen, that means very cooled air at very low temperature into it so that the food freezes. Indirect contact is the food is placed in direct contact with the cooled metal surface, but the freezer solution is put in, and direct contact is the food material comes directly in contact with the refrigerant, which is the liquid nitrogen or the freon or the carbon dioxide thing. This is faster, expensive, and it freezes individual food particles. The indirect contact, where you're putting it onto a metal surface, is relatively faster and it is more expensive. So in the next slide, I've just tried to show you the schematic for the indirect contact freezing system, where it is put onto a plate, and here the refrigerant is circulated, so the food gets frozen because this plate goes to very low temperatures, and so therefore the food is frozen. So this shows you indirect contact. In terms of direct contact, you have the food and the refrigerant circulates. The food is in direct contact with the refrigerant, and the food will get frozen. You can also do direct contact freezing by keeping the food in conveyor belts and by actually using liquid nitrogen through the nozzle to freeze the food. Then you have chilling, which is similar to freezing, but here it only brings down the temperature, and this only prevents the microorganism, that is the rate at which the microorganisms multiply. The disadvantage of chilling is several microorganisms can grow. There are the chilling temperatures that are commonly used are between -1 to +1. You use for fresh fish, meat, sausages, ground meats, etc. From 0 to 5, it is for pasteurized canned meat, milk, cream. So you see, we always keep milk cream, yogurt, the salad we make, sandwiches, unused pizza, all we keep in the refrigerator. So your refrigerator temperature must be between 0 and 5. For 0 to 8, if you keep your temperature, you can keep your cooked meats, fish pies, butter, margarine, hard cheese, even cooked rice, fruit juices, and soft fruit. However, if you keep the cooked rice at plus 5 degrees or at plus 1 degrees, you will find that it will keep for longer. So food irradiation is um, used for preservation, and FSSAI has rules and regulations for the food irradiation. But the common man has different concept, perceptions, because they also always think that radioactive is dangerous. But in India, if think before I come to what food irradiation is, all the irradiation facilities, anybody who has an irradiation facility has to be approved, and you must have the license of the Atomic Energy Radiation Processing of Food and Allied Products Rules 2012. So before you want to get an FSSAI registration, you would want to get the license and approval from the atomic energy. Okay. The effects of irradiation are: it is used for disinfestation, it is used to enhance the shelf life of fruits and vegetables, and it is also used to improve the shelf life by inactivating the spoilage microorganisms. So, what is an ionizing radiation, or what is irradiation? These are radiations which cause disruption of the internal metabolism of cells. They cause DNA cleavage, which results in loss of cells' ability to grow and multiply. It may produce free radicals, which, upon contact come into contact with food. The free radicals in the food will again cause cellular damage to both the microorganism, and the DNA is considered the radiation sensitive portion of the cell. So in irradiation, it is the DNA of the microbial cells which is targeted to prevent the growth of the microorganism. The ionizing radiations, they exist in the form of waves. So the shorter the wavelength, the greater the energy. So if you have seen the electromagnetic spectrum, you will see that you have light waves, radio waves, microwaves, television. These are long wavelength. So low energy cannot alter the structure of an atom. The shorter wavelengths have got higher energy or greater energy, which is sufficient to knock off an electron to form a free radical, but not high enough to split an atom, which is known as radioactive. So in the ionizing radiation that we use, what it does is it only knocks off the electrons producing free radicals, which can cause the damage of the DNA. It is not radioactive. So you need to educate people that the ionizing radiation which is used for food is not radioactive. And the free radicals that are produced because the electron is knocked off interacts with DNA, which is responsible for the killing effect of the ionizing radiation. In the ionizing radiation, it is the gamma radiation which is commonly used for the preservation of foods. It's the most widely used ionizing radiation. It can penetrate and it emits in all directions. Generally, a gamma irradiation facility uses cobalt 59 thing to neutrons in a reactor, and the reaction it produces cobalt 60, And cobalt 60 is what is used for radiotherapy, for sterilization, and for food irradiation. Now, in the food irradiation, the dosage of the food irradiation is important for the different effects, the preservative effects that irradiation brings about. So, low dosage application is actually the doses are generally measured in kilograms. Okay, 1 kg is equal to 1000 gray. So the low dose applications are up to 1 kg. They are used for to control insects, to inhibit maturation, and also to inhibit sprouting. A large number of seeds are irradiated so that sprouting is prevented and they can be used in the time frame that in the season, the seasonal crops. Medium dose application is from 1 kg to 10 kg. This is used for extending shelf life and for reducing the microorganism level. Above 10 gray, it is used to sterilize, which is similar to canning, and it is used to decontaminate, especially the spices. So FSSAI regulations, they have actually given the limits of the dose and the radiation. Every facility has to be registered and have the license under the Atomic Energy Radiation Processing Food and Allied Products. The person who operates the radiation unit, the personnel, they have to have minimum qualifications. They have to undergo training at the Atomic Energy Commission, and they have to have a certification. According to the regulations, radiation processed food cannot be sold in the open. It has to be prepackaged. And the label on the food also has to carry these two labels. All should have the label, which is this signage, which should be in green, and they should have the name of the product, the purpose for which radiation was carried out, the operation license number, the batch identification, the date of processing, and also they have to indicate what type of ionizing radiation that they have used. So it is very stringent, the irradiation regulation. It comes under 2.13 in the compendium on food additives. So this is the classes of foods they are allowed. So bulbs, stem, root, and tubers to inhibit sprouting, fresh fruits and vegetables to delay ripening and shelf life. So you see they have given the limits. So this is the very low grade cereals for insect disinfectation, and the fish, you see it is at the medium from 1 to 7. So this again is for shelf life extension and to control the parasites. Meat is again from the medium, and only dry vegetables, seasoning, spices, you see only this one has gone to 14 kilo gray. That is the highest which is permitted. Okay, and for packaging materials, food additives, and for health foods also the limits, dose limit of the radiation is provided. Then you have high pressure food preservation. Just like you have high temperature preservation, you have high pressure food preservation, where you apply a high pressure up to about 900 megapascals to kill the microorganisms. So what this high pressure does is it delays the onset of chemical and enzymatic deteriorative processes, and the advantage here is it preserves without degrading the vitamins. And then you have pulsed electrical field food preservation, where here you are applying an electrical field of a very high electrical field of 20 to 40 kilovolts per centimeter, but you give this in pulses at various intervals of time. Generally, it is less than 1 second. So the pulsed electrical field is there. It's called pulse because it is given at various time intervals. So what is the effect of PEF? It actually prevents the bacteria from growing, because the electrical field, when the bacterial cells are exposed to that, either it causes a rupture in the cell membrane or it causes holes, very similar to what we use, electroporation. Those of you who have done electroporation, you will know that we give electrical pulses. This advantage is the taste, flavor, and color are retained. It is not toxic. However, it has no impact on enzymes and the spores. It can be used to treat liquid foods only, but it's very expensive and it is very energy extensive. Then you have the older methods that we used, that is pickling, putting them in vinegar or in an organic acid. So here the pH is brought down, so it prevents the growth of the bacteria and the microorganisms. A second method was to use fermentation. So when we used fermentation also, what would happen is microorganisms would use the carbohydrates to lower the pH, and then you put in your products and microorganisms are prevented from growing in the fermenting media. So the fermentation, different types of fermentation in the by the organisms are alcoholic fermentation, where the end product is ethanol; vinegar fermentation, when the end product is acetic acid; the homofermentative lactic acid, where lactic acid is the only product; heterofermentative lactic acid, where it produces lactic acid, acetic acid, ethanol; propionic acid fermentation, which produces propionic acid; butyric acid fermentation, which produces butyric acid, acetic acid; mixed acid fermentation; and 2,3-butane-diol fermentation. So what you see over here is that it is the acids, which are the products of the fermentation, which will bring down the pH. And this lowering of the pH prevents the growth of the pathogenic bacteria. Uh, okay, let's go. And then you have the chemicals, preservatives, which are added, and you have gone through this, we have gone through this. So here the preservatives are added, one, to prevent the growth of the microorganism, or it is to prevent the oxidation of the product, or it is to prevent the enzymatic process of the product, to inhibit this. So if you look at the first preservative that was used, chemical, it was salt. So salt was added to preserve foods, because when salt is added, salt takes up water, so water will not be available and the water activity will be reduced. When the water activity is reduced, the water is not available for the microorganism to grow. So salting was used in meat, cheeses, and bread. This was done way back, even by the cavemen who did salting. Then you have curing, which is again adding salt to the food, and in addition to salt, adding nitrites and nitrates to inhibit Clostridium botulinum. Smoked fishes also are cured. So smoking also was done to prevent the growth of microorganisms and prevent further degradation. Sugar, just like salt, when sugar is added, The sugar takes the water, so the actual water will not be available and the water activity is reduced. And so when water activity is reduced, microbial growth is reduced. In the presence of acid, when fruits and vegetables are added, it lowers the pH. So the jams and jellies are all preserved by the high content of the sugar. The high content of the sugar and the cooking that is used in the beginning prevent microbial growth. Then you have the different antimicrobial agents such as sorbic acid, which is used to preserve a large number of foods such as cheese, bakery products, etc. Benzoic acid and sodium benzoate, which are used to preserve large number of vegetables, fruits, brings down the pH. Sorbic acid brings down the pH. Lactic acid brings down the pH. Parabens, which is para-hydroxybenzoic acid, also brings down the pH. It is used to preserve cereals, etc. Nitrite is used to preserve meat, sulfur dioxide, and sodium sulfite for dry fruits. Antioxidants, the mode of action is to remove the oxygen. So therefore, oxygen will not be available as a reactant to bring about the oxidation reaction. So the antioxidants are generally used in fats and oils which contain the saturated and the unsaturated fatty acids, which can easily be oxidized. So the antioxidants that are used are BHA, butyl hydroxyanisole. You see, it is mainly for butter, lard, baked goods, potato chips. BHT, butyl hydroxytoluene in fats and oils. Vitamin E, a natural antioxidant for preservation of fruits. Galates in fat and oils, and ascorbic acid or ascorbyl palmitate for preservation of sausages and chicken broths. Then we also have anti-enzymatic agents, like for preventing browning, or it removes the metals which are required for the enzymatic action, especially browning reactions, the meladine reactions. So most of them are natural compounds such as citric acid, ascorbic acid, EDTA, polyphosphates, which are added as anti-enzymatic agents. And then finally, now we come to what is the new technology that is used in food preservation, which is known as the hurdle technology. Hurdle technology is the combined use of several of these preservation methods that I described to you to make a product which is self-stable and to improve the quality. This is also known as combined method technology. Leisner in 1976 introduced the term hurdle effect. So what is this hurdle effect? We have looked at all the preservation methods. You see, either it, prevents a chemical process of spoilage, or it prevents microbial growth, or it prevents a physical growth, or it uses the two. There is no single preservation method which will address all the food spoilage and food pathogen effects. So hurdle technology is to try and use as many of these hurdles to prevent the growth of microorganisms, to prevent chemical spoilage, and to prevent physical spoilage. So you use all the hurdles. You can use chilling with low water activity, or with the modified atmosphere, and treating with a chemical. Now, using many hurdles, you should be able to have a very safe product with a very long long shelf life. So the microorganisms should not be able to jump over all the hurdles present in the food product. So all the preservation factors that we discussed, they prevent microorganisms from multiplying and causing them to remain inactive. The hurdle concept illustrates that complex interactions of temperature, water, pH are all significant to the microbial stability. So you should use more than one thing to prevent the growth of the microorganism. So here is an example of a hurdle technology which is used for some canned meat. So you see, the hurdles are being added one at a time. So the first hurdle was to have a pH of 5.2 to prevent the growth of microorganisms. The next was to reduce the water activity so that certain microorganisms cannot grow. In addition, you do a pasteurization at 70 degrees for 2 minutes to kill some microorganisms. You can also add preservatives at low quantities like the salt, sugar, and nitrite. You can further chill it, keep it directly from 70, bring it down to 3, and you can store it in modified temperature. So here in this case, what you're taking care of is you're taking care of extrinsic characteristics. You're putting the hurdles for the microorganism, and also you're using intrinsic characteristics and you are adding the hurdles. So as we add the hurdles, you see the microbial growth keeps decreasing. Okay, this arrow shows this is decreasing. So finally what you have is, as you increase the number of hurdles, the microbial growth is decreased and the shelf life will be increased. So this is what hurdle technology is. So tomorrow's class will be on basic principles of work in analytic laboratory and classical methods of analysis. This class, I apologize, was very long because it involved two very large subjects, that is food preservation and food spoilage, which should have been independent, and the next time we will try and make them independent. Thank you.